Hello everyone, today I'm going to show you the inner workings of a few models of these mechanical calculators. And basically they all, or let's say most of them, are based on the principle that Leibniz invented in 1680 or around that time, which is called today still the Leibniz wheel. So I've taken this Lindstrom calculator, this big black one, because it's really big, it's older, so you can really see the workings inside, and it's easy to recognize what I'm gonna try to explain you. So what we have inside is, for each dial, we have this special wheel, you see, which is all the teeth of the gear wheel are not all long the same. Some are longer, some are shorter. So the idea is that by pushing the numbers here, I have another gear wheel in the back, you see, that is moved a little bit up. If I push 2, it's moved up more, 3 even more, 4, 5, and I can go up to 9, which puts it in the highest position. So let's say I am in position 3, I turn my crank, and the gear wheel is in such a position that it will hang on 3 teeth of this gear wheel here. You can hear it. 1, 2, 3. So what happens? What happens that the dial will turn 3 position and go to number 3. So up to now there's nothing particular. Now if I want to add 4, I put 4, and you see the back gear wheel is moved 1 position up in such a way that it will hang on to 4 of these teeth. So I turn, you can hear it, 1, 2, 3, 4. But since I was already in position 3, I do another 4 positions and I get to 7. And that's the sum of 3 plus 4 makes 7. And this is just the easy, simple principle on which these machines work. So in this case, by moving my wheel, my back wheel, up and down in such a way that when I turn here, I will hang on to, if I'm in this position, I will just hang on to the first tooth. If I'm here, it's going to be 2 teeth. If I'm here, it's going to be 3, 4, 5. And in this way, we can do all the operations we have seen in a previous video. And the same goes for subtraction. Now, this particular machine has a special way to do that. So I just have to move this lever here to go from addition to subtraction, and it will move something inside. I'll show you in another video. It'll move something inside here in such a way that this is going to turn the other way around. But most machines, you just turn the crank the other way around. So let's say I am position 7, and now I move it to subtraction. I write 4, so from 7, now the gear wheel will move 4 times in the opposite direction, and that makes 6, 5, 3. And there we go. 7 minus 4 makes 3. And on this basic principle, easy principle, we can do all the 5 operations I've shown in a previous video. The only small difficulty which had to be overtaken back when people were developing these machines is the carry mechanism, because we know exactly that if I do 6 plus 7, that makes 13. So in this wheel, we have no problem, because the little dial inside will do 7, 8, 9, and then it's done a whole turn. It's go to 0, 1, 2, 3. So it goes to 3, which is 13, that's fine. But when it goes over 9, there's another little mechanism inside which will make the next dial do 1 little turn, so that this one moves to 1. And that we'll see now. If I do 7 plus 6, I do 7, 8, 9, 0, 1, 2, 3, and the other one does another 1 in the end. And in this way we have done the carry mechanism, and that's fantastic, because with this simple, very basic, simple mechanism, easy to understand. It's really mechanical. It's just the number of turns that we do with these Leibniz wheels or Leibniz cylinders. We can do all the operation including the square root. We can do it in a much easier way than if we had to do them by mind. So that was about it for this calculator. I will show you now these other calculators and how they work in the inside, but I need a little time to prepare the cameras. Okay, I go on with the explanation of the inner mechanics of these calculators. Here we have a pinwheel calculator, an original Ordner, and I have already taken off the screws off the top. So what we have inside is this cylinder on which all the pins are mounted. Now, let's go again to the beginning. Reset everything. I put down here a few numbers. 3, 4, 5, 6, 7, 8, 9. I turn the wheels this way. So what happens here is that if I turn it, you can see there's a lot of pins here that have been pushed up. And how many of them? In the case of the 9, all of them. In the case of the 3, we have the first 3 which are pushed up, and all the others are still inside. So these pins, when they turn and they get here, they connect to these gear wheels, which in turn will turn our dial numbers. So where I have put 3 pins come up and 3 pins will turn the wheel 3 times, 3 teeth. Where I put 9 pins come up, and the wheel turns 9 times. And so that's the way the number is brought down here. And the rest is the same as we've seen before. What we have here also, which is interesting, are these moving pins. You see, they can move. They have they go back, but they have possibility to move left and right. So what is their purpose? So let's say I do an operation like 5 or 6 plus 6. That makes 12. That means that the next wheel will have to turn to the position 1. So how does this happen? They have developed a very ingenious mechanism on the Ordner. It happens this way. When this wheel gets to 0 on the next step, you will see something happening here. I'll try to get as close as I can. I hope everything stays in focus. A little lever is pushed forward. This lever in turn, now you see this is the moving pin. This moving pin is being deviated from its position in order to make the other wheel turn. You see now it's deviated. You see it goes back and forth. It's deviated and allows for that one to make one turn. And so I go to 12. And this is how the carry mechanism works. And it's quite ingenious. It's very nice to see, for example, if I do 1, all the 0 minus 1, that means that 0 minus 1 makes 99999 for the mechanical calculator. You will see all these levers coming up to make the carry mechanism go all the way down to the bottom. They all came up and now they are pushed back at the end of the turn. One more time. I go a little bit closer. Voila. Now we have 2 sets of these moving pins. One is the one I showed you before, but we have another one here. It's a little bit between the gear wheel, but you see these are also all moving pins. They can move back and forth. And what do we need them for? We need them because the carry mechanism has to be done the other way around when I do a subtraction. So let's say I do 43. And now I take 5 off. I do a subtraction of 5. So we have to go to 38. So this lever, has to move to the 3 position. Okay, here I put 5. And I turn now anti-clockwise. So what happens? The same thing happens, but the other pin is used. 2, 1. Now with the 0, we will see the lever coming up. Oh no, with the 9. Okay, there it goes. It has come out here. You can see it, this lever here. And now this lever intercepts the moving pin, which you can see coming. There it comes. And moves the other dial to the 3. And this way, the subtraction, the negative carry is done with the subtraction. Okay, that's for how it works, the pinwheel calculator. Now we move to this calculator, which is it's still a pinwheel calculator. It's just a little bit of a masked mechanism. I chose, normally the original model of this type of calculator is the facet we have there. But I chose the Precisa to open it, because for a practical reason. Precisa just asked me to take off 4 screws, whereas with the facet I have to take out 8 screws. So basically this is the same exact mechanism as the pinwheel mechanism we just saw. Just the difference is here, when I have to move around with the carry mechanism and with the multiplication and divisions, I move the carriage on which the result register and the counter register are positioned. Where here, the result register, which is this one, and the counter register, which is this one, they don't move. They stay where they are. What is moving is the input register. Now I input a number, you see? Okay, 57964. This is moved, and then I can input my number in the output register. And I can move it the way I want, back and forth. See? So instead of moving this whole part as I would do here I'm just moving the input mechanism, making things a little bit easier. The rest, the all inner workings of the 2 registers, that you cannot really see them well. I should disassemble the whole thing, which I don't want to do now. But everything else works exactly the same, or mostly exactly the same, as in our original Othner pinwheel calculator. One interesting thing about this specific calculator is that you remember when I showed the operations, when I inserted a number to make a division, I inserted a number, then I had to go and clear the counter register. Well, in this model of Precisa, they have developed another special mechanism. I have the button division here. I push this button, everything moves to the left, as would happen with the facet. But when I input the number the first time for doing my division, you will see the counter register doesn't move at all. So you don't have this hassle of remembering to clear the counter register. And that's, for the rest, it just works almost exactly like a pinwheel calculator, but the input is much easier. On the other hand, this type of calculator can hardly do a square root. And we will see in another video why that is not easy with this type of calculator. You can do it, but it's really complicated. Okay, this for the facet type calculator. Let's go to the last one, which is the Monroe type. I have disassembled the carriage. You see on the inside, this would be normal carriage we've seen before. On the inside, we just have a series of gear wheels with the number wheels mounted on them. And that's about it, what we have here. So here on the mechanism, you see these wheels here. I point them with a little stick. These wheels here are the wheels that will transmit the input to the carriage. These wheels here. And how do they do them? So, if you watch inside here, you see a series of discs. Now if I push number 1, these discs move a little bit. Number 2, number 3, number 4, number 5. They move a little bit back and forth. So when I push number 1 and I turn my crank, you see some wheels, gear wheels appear there. And they appear in a way that only one tooth will connect to our upper gear wheels. You see now, like you can hear it? click. They did one turn. Now let's go position 3, for example. I do it on more than one column so that it may be more visible. Now I have input 4 times 3, 4 times on 4 columns the number 3. I turn. Now the gear wheel, the first gear wheel, is still in the same position, doesn't hang on, but the second gear wheel has moved a little bit. And we'll do 1, 2, and 3 turns. Let's go to number 9. You see, they move a lot. Number 9. And now if I turn, both gear wheels will connect to the upper gear wheels and transmit the number 9 teeth movement to our number wheels on the carriage mechanism here, on these ones here. And in this way I can input the number it's on it. It's still again another representation, another way to set down what we have seen before very clearly on the Lindström, but it's still working on the Leibniz wheel. It's just set up in a different way, which actually gives the Monroe a little bit of an advantage, because the Monroe are, among all these you see here, are the lightest, still weighing around 3 to 4 kilos, but they are the lightest. And they are faster, because here the crank just turns a little bit. You see, it's a little turn, whereas here I have to turn a lot more. So I've done some competitions with my students, and we've always seen that most of the times this one is the fastest. Sometimes this type is fast as well, because the input mechanism is very fast. I can just write on this. I don't have to go like here to choose the numbers on all this big keyboard. Here I just have the numbers 1 to 0, 1 to 9, 0 to 9, let's say. And so it's easy to input, but then still I have to turn quite a lot. Whereas here, once I input the number, I can turn a little bit and everything works very fast. But then it's just taste. I've seen students who would never take a Monroe in hand because they consider them primitive tools, whereas they love the Ordner. Others just fell completely in love with the Facit or the Precisa. So it's just a matter of taste. Well, that's about it. Thank you for listening.